Okay. I I should have made a comment when we started. Okay, so I should have made a comment that there's this velocity that we talk about in Darcy's equation is not a physical velocity that the oil is moving at. Okay, it's sometimes an important differentiation. The Darcy velocity is the volumetric rate, which I'm writing QR, okay, or QOR, the local volumetric rate in the reservoir, in the rock, divided by the total bulk cross-sectional area to flow. Okay? So in the case of our well, it was 2 pi RH. But that's not the area where fluid is actually flowing, because there's like the rock where there is no fluid flowing, and then there's the pores. Okay? So then there's something called pore velocity, which is not used in the rate equations, it's not used in Darcy, but sometimes it's very important, and that's when we're concerned about how long does it take for something flowing here to reach the wall in real time. Okay, because we know the distance from here to the wall, we want to know the velocity that we can calculate the time of arrival 10 meters or 100 meters away. So it's usually enhanced oil recovery methods where we're injecting something and we're producing, and we want to calculate how long it takes for us, what we're injecting, to reach where we're producing. And then you have to use the pore velocity. And the pore velocity divides by the actual flow area, which is the bulk flow area times porosity. Okay? There's probably some saturation should be in there too. Okay? Because like if the pore was 50% filled with water, right, that was not moving, let's say kind of initial water is not. So I think you need 1 minus water saturation also. So, okay. But the point is that velocity is going to be higher than the Darcy velocity by some considerable amount usually. Okay, so that was, so basically this is usually used in connection with EOR only. Okay, now the next thing that we have to deal with are units, because this is a real mess. Okay, units. When it comes to the rate equation and Darcy's equation and everything. Okay, so if we use pure SI, of course that's the simplest, and then we're going to have rate in cubic meters per second. Height would be meters. Viscosity, Pascal second. Formation volume factor doesn't have units usually. See, what else do we have? Pressure, Pascal. So what else is in our equation? Radius cancels, but we can say the distances, h and radius meters. Yeah, K. the unit of K, if you put in all of these other units together, is meters, would be meters squared. For a pure SI treatment, would be meters squared. Okay? And if you ask me, for the life of me, what is 100 millidarcy in square meters? Without a pencil, I probably have a hard time giving you the answer. Okay? I would struggle. But I'll give you some conversion. We don't usually use meter squared, but we'll show you that. Okay. So, is this all the quantities in the equation? K, H, pressure, that's everything. Okay? And because we're doing it in, velocity, that would be meters per second. And of course, rate could either be at reservoir conditions or surface conditions. It doesn't matter. Okay. So if you use pure SI, then you don't end up with any extra constants. But you end up with the quantities. Nobody uses seconds for time. Nobody, ever. Okay, so even if you use all of the Pascal and meters, that's it, right? Pascal and meters, the fact that we use days for our time unit is going to throw in a constant, however many seconds in a day. Anybody know that? 28,640, I don't know, it's something like that. It's some big number. So you're going to get this constant in there, regardless. So since we have one constant, we might as well do it so that we can use our favorite units, okay? So we basically have what I'm going to call metric or quasi-SI, okay? And then you've got field units. Okay. So there's actually a and then there's going to be something we call Darcy units. It wasn't really Darcy who used the units, but it was the Botset and Muscat, these guys who decoupled the K and the mu. So we kind of got three sets of units. So for velocity, it's centimeters per second. Rate, cubic centimeters per second. Area, square centimeters. Length, would be R, for example. H, centimeters. Pressure, atmospheres. And they didn't deal with viscosity, centipoise. B, they didn't use, it doesn't have units, so it doesn't matter. And then K. Okay? So for this set of units, what we call Darcy or lab units, you could say, old lab units, this has the unit D, which stands for Darcy. And it's actually a capital D. Okay? Capital D. I wanted to put SI in here, but it's, let me just try to do that. Okay, so metric, that would be like in Norway. They're kind of SI, but not really, okay? So here we would use cubic meters per day, or meters per day. Cubic meters per day. Square meters, meters. Here we use a non-SI unit. Bar is not an SI unit, 10 to the 5th pascals. We'll probably use centipoise. Well, we will. But centipoise is exactly equal to millipascal second. So you could really say we're using SI, and we're just taking care of the millis and the kilos and the stuff like that. But so this is 10 to the 5th pascals. B doesn't have a unit, and then permeability is usually, it could be one of two. It can either be Darcy or more commonly millidarcy. And we use little d. It's M for milli and little d for Darcy. That's the SB nomenclature. Okay? It's not little m, big D. Okay, so it's usually millidarcy. And these are all going to be the same for oil or gas. Okay? But when it comes to field units, which is like Oklahoma, Texas, cowboy country, it's going to be two different sets of units. We got gas, we got oil. Well, let's take oil first, since okay. So for oil, feet per day, feet per day. We don't talk much about velocities in Oklahoma, except it's miles per hour, and that doesn't really apply down in the reservoir. Okay, that's the only velocity we usually talk about. Oil stock tank barrels per day, all the time. We like to multiply directly by that 40, okay, to get our money. But on gas, you've got many different 1,000 standard cubic feet per day, million standard cubic feet per day, or possibly just standard cubic feet per day. Like the book Well Performance that Professor Golan and I wrote back in '86, we consistently use standard cubic feet per day. Okay? The paper by Fetkovich that you're going to be reading, MSCF per day, 1,000 standard cubic feet per day. Okay, that's what he uses. So you've got three different ones, and then million is the more kind of day-to-day. We talk about, that well made 3 million a day, 3 million standard cubic feet per day. Area, feet squared. Actually, when it's the same, I'll just put the same. Feet, PSI, centipoise, nothing, and again, it's either Darcy or millidarcy. Most commonly it's millidarcy. It might be Darcy. So this equation that we derived up here, assuming there's no mistakes in it, this would be for pure SI, using seconds as time and so forth. Okay. Now the question, and the good question on, not the exam, but the good question if you want to sharpen your mind, is how do I go from this to one of these like field units or local metric units in Norway? How do I go from that pure SI to something that I use with bar and days? Huh? You have conversion factors, but the thing is that there's two things about this equation. The input numbers it expects are pure SI. It needs meters squared permeability. You're never going to find that number anywhere. Okay? You want to put in millidarcies, for example, in Norway. So you want to input millidarcies. Meters is okay here. Bar, but this equation, the way it's written, it expects Pascal. So if it's 300 bar, I have to write 300 times 10 to the fifth, right? Okay. But if I want to write an equation where I can just throw in 300 number, then it's the opposite. You have to do something to get the extra 10 to the fifth in there. Okay, so it is messy. It's complicated to get that correct. I'm just telling you. And then when you get all the things on the right-hand side, input with, centipoise, and you've got the millipascal second conversion and so forth and so on. When you get all that done, what it will calculate is cubic meters per second. Even though you put bar, millidarcy, and all these things here, it's going to calculate with this equation cubic meters per second. Then you're going to have another conversion to go from cubic meters per second, which is like a really small number, to cubic meters per day. So there's another conversion on the left-hand side. So it's messy. All I'm telling you, it's messy. Now, obviously, none of you probably are going to be ever required to do this. You're just expecting to see the number, okay? So I can just show you the number, what it'll be. If we go to field units, I can tell you the number. If you go to bar and millidarcy, I'm not sure what it is. I can tell you for a couple, I just know the number because we grew up with them, okay? So, for example, for field units, oil, QO is equal to 141.2 mu OBO log RERW KH PE minus PWF. That I can guarantee. Well, so stock tank barrels per day is what it gives you. We input the number here in millidarcy, feet, PSI. Of course, it doesn't matter if it's PSI a gauge. Centipoise, no unit, and this, of course, is no unit. Just don't use RE in feet and RW in inches. Which on the exam I might give you RW in inches and RE in feet. So it sounds stupid, but you have to be careful that you're using the same units here. Okay, so that's what you get if you do this. Now, how to get the 141.2? That's the tricky part. I don't even know if I want to try, but do you guys want to see it, or do you just want to take it as a good goofisk? Yeah. It's guaranteed not something you've learned in high school and college. I mean the whole process of doing it. So at least it's something new. All right? How do we do it? Okay, so we start with the original equation. 2 pi K meter squared H meter delta P Pascal viscosity Pascal second. BO can forget, and log RERW you can forget. Okay, so we can kind of drop that one and that one because there's no units. Okay, we have to keep track of the 2 pi. So what we want to do is we want to have some constant C so that we can input K in millidarcy. We want to input M in meters, not meters, but feet. These are what we want to input, delta P and PSI. Viscosity in centipoise, and that's it. And then what we want calculated out here is stock tank barrels per day. This is what we want, and this is what we have. Okay. Okay. You can kind of go from it one or two ways. What I'm going to do is I'm going to say that I want the input in millidarcies. Okay? But as soon as I put that number in, I'm going to do a conversion to get it to square meters. Okay? So the question is, how many meters squared for permeability? How does it relate to millidarcies? Okay. So it ends up that one Darcy, which is 1,000 millidarcies, is made in the SBE. They've made it exactly equal to, even though it's not exactly equal to, they just say that it's okay to forget the 3% error, okay? Because permeability ranges from, so many orders of magnitude. If it's off 3%, good enough. So they basically say that 1 Darcy is exactly equal to 1 micrometer squared. Okay? Which is equal to how many meters squared? Right? So 1,000 millidarcies is equal to 10 to the minus 6. 10 minus 12, thank you. You got to square that inside. That's the same as, thank you. Okay, so we got 10 to the minus 12 meters squared is equal to 1,000 millidarcies. So 1 millidarcy, right, is equal to how many meters squared? Okay, all right, so that's the conversion unit we need. And let's see. Maybe easier to see if we actually put in numbers. So let's say that our permeability is 1 millidarcy, okay, and our thickness is 1 foot, and our delta P is 1 psi. You know, we could put in 326 psi, but I'm just going to pick number. Okay, and viscosity is 1 centipoise. So for me to use the equation that we have, we write 2 pi, and then we put K. Well, K is 1 millidarcy, okay? But to use that equation, I need that in meters squared. So I need to multiply, there's 10 to the minus 15 meters squared per millidarcy. We agree? Okay. And when we do it that way, you can see that one disappearing. Now, if I would have put in 23 millidarcies, it would also do the same thing. Okay? So the point is that I'm going to be putting in my numbers with this. I just need to know what is C. Well, C is going to be the 2 pi, it's going to be the 10 to the minus 15, and all the other things. H, it's 1 foot. So I put in 1 foot. And I'm obviously going to have to move this. Okay. I put in 1 foot, but I need it in meters. There's 3.28 feet in a meter. That's just something I know. 0.30 something, 4 meters per foot. Okay? I just know this is the conversion. There's 3.28 feet in a meter. So I put in my actual value. It could be 23 feet or it could be 1 foot, whatever. But this is going to cancel out with that. And then what I'm left with here is meters. Okay? And then delta P. I put in 1 psi, but I know that there are 14.50377. I know it's I don't know why I know that number. I can't remember my phone number. But per bar. Okay. So I put in the actual delta P is 3,000 psi. Okay, or whatever it is. I'm going to put it in psi. But when I put in that number, I want to automatically convert that to not bar, but Pascal, right? So that's going to give me bar. So I need to know. I need more space here. There's 10 to the 5th Pascal per bar. So I can cancel that. And now I'm left with the pascals that I need. Okay. And then down on the bottom, I'm going to put in viscosity, but I'm going to put in 1 centipoise, or whatever the value happens to be, but I'm going to put in centipoise, 0.05 for gas, something, 0.5. I'm going to put that in. And then this is 1 centipoise is exactly equal to 1 millipascal second. Okay? And what we need is Pascal second. And there's 1,000 millipascal seconds per Pascal second, right? I just know these things. I mean, if you look them up in the table, you'll find out that's correct. So that'll cancel that. That'll cancel that. And we'll end up with the number we need in our equation is that. This is going to give us cubic meters per second. Okay? If we put in the permeability in millidarcy, the thickness in feet, pressure in psi, and viscosity in centipoise, then the number we calculate on the right, 2 pi times all those numbers, will give us cubic meters per second. So far we've got 2 pi, let's just add them all together, put them all together, 10 to the minus 15, 1 over 3.28, 1 over 14.5, 10 to the 5th. Down below we've got 1 over, that would be 10 to the minus 3, right? And there. Okay. Times K in millidarcy, H in feet, delta P in psi, and viscosity in centipoise. Okay. But what it calculates is in cubic meters per second, which is not what I want, right? God, what a mess. Okay. Okay. That gives us cubic meters per second. So if I get this number in cubic meters per second, which is just not the number I want, I need to multiply this here times all of that there. I'm just going to copy this cheat. All right. That gives me cubic meters per second, right? So if I take that number here and I convert the cubic meters to barrels, I think there's, I always get this, 6.28 barrels per cubic meter, I think. Okay? Pretty sure that's right. I hope. Okay, that'll cancel that. No, that's not what I want to do. My goodness. .28 stock tank barrels. Is that correct? Does anybody know the conversion for cubic? Yeah. Is correct?
6.289.
All right. Okay. Stand correct. Anyway, at least it's not the inverse of that. I didn't want to be off by that. Okay, so that's okay. Then we can cancel that, and now we got our stock tank barrels per second. Happy? No. So we got to go to the seconds thing. So we need 24 seconds. 60 seconds in an hour. No, 60 seconds in a minute. 60 minutes in an hour. 24 hours in a day. That's how many seconds there are in a day. And then we can cancel that. Okay? So, this is where I go to church. I go to church and make a little prayer, because if I'm lucky, it'll work, and if I'm not, it'll just prove again that all right. So we got 2 times pi, 3.14. Times 10 to the minus 15 divided by 3.28 divided by 14.5 times 10 to the 5th divided by 10 to the 3rd times 6.289 times 60 times 60 times 24. Then we got to flip that upside down. Remember how I wrote the equation? Oops. So this times this times okay, this whole thing here ends up being 1 if you put in all the digits. Okay, so that's where you get that constant. Okay. And that's giving us QO in stock tank barrels per day. Okay, so it's a little bit messy, but you've done it with one, then if you understand this, then you can do it with any other. Okay. Now, I want everybody in the next 5 minutes to do the same thing for the quasi-SI Norwegian metric units. And if you don't get it right, you can't take the exam. Why do you think I'm joking? Everybody smiles. No. So you don't have to do that. But you could do it for your own sake. Because I don't know what the equation is for Norway, to be honest. I mean, standard cubic meters per day, millidarcies, bar. So it's something worth doing. I would do it. But, I mean, it's just a waste of everybody's time for me to do it. So you can do that yourself. You have the recipe for doing it. You simply have to get what are the conversion factors for bar. Yeah, so you kind of have it here, but I'll let you guys do that, okay? By the way, this inverse of is doesn't really matter. Okay, any questions then? That's kind of. We've now kind of come up with the very important oil rate equation for the simplest assumption of, constant mu, constant B. We've done the units conversions. What I will, just because I'm going to stop talking about oil kind of at this point, and we're going to move over to gas next week, is that real oil how does mu and BO, it's actually the product, vary with pressure? Okay, because if it's a strong function of pressure, you have to bring that inside the integral, right? Because what we really have is we just took dP and we had 1 over mu BO because out on the outside because it was constant. But the real, and you could actually, for your PVT problem that you're working on now, you could plot 1 over mu BO. This is the bubble point. It's going to look something like that, and it's interesting because it's fairly constant, because the pressure dependence of viscosity by itself kind of balances the pressure dependence of BO. So you get something that's more constant than mu by itself or bo by itself. So they kind of cancel out each other. And this is in the undersaturated part. So if our external pressure is out here and our bottom flowing pressure is in here, then basically we can use some kind of average here as a good approximation and just use delta P. So this is okay. But what happens if you go below the bubble point? Everything gets more complicated because you have two phases. You have oil phase, you have oil relative permeability. So now the permeability, you've got KH out here. Now KO is not constant. It's, depending how low you go in the pressure below the bubble point, you get more and more gas. The oil permeability goes down, down, down. So in a real problem, so this is okay for pressures above the bubble point, but if you look at KO over mu OBO, this function here below the bubble point will drop down approximately, this being 0, approximately like this. Towards 0. From whatever it is at the bubble point, it'll kind of approximately linearly. It could be nonlinear, but approximately it'll look like that. So now, if the pressure, now we have to do an integral of KO mu OBO. So now if your bottom flowing pressure is here, okay, then it's the area under this curve that you have to multiply. You have to rewrite this equation here as K absolute H 141.2 log RERW. Those are the only things that are constant. And then we have to multiply that by the integral from PWF to PE of K relative permeability to oil mu OBO dP. Okay, because the oil relative permeability gets worse and worse as you lower the pressure below the bubble point. Gas coming out of solution, oil saturation is going down. That's shown graphically here as the area under that curve there. And as a first approximation, you can simply draw a straight line down to 0, 0. Okay? Who actually treated this problem first? Muscat in 1940, I don't remember the year, during the war, I think. Muscat and a guy named Evinger. Maybe Norwegian. Okay? So that's for oil. That's all we're going to talk about oil. We'll move to gas next week.